Hello everyone. Today I am going to describe about the thin film interference. So this thin film interference are responsible for colors of soap bubbles, oil sticks, changing colors of peacock feathers, blooming of camera lenses and so on. Now when light impinges on the first surface of a transparent film, a portion of the incident wave is partially reflected and partially transmitted. The transmitted portion is then reflected from a second surface and emerges back out of the film. Thus, two waves are emerged from the thin film. First one, wave reflected from the front surface, and the second one, wave reflected from the rear surface. The two waves have different optical path lengths which are determined by the width of the film. The two waves will eventually interfere, and the interference pattern observed will depend upon the thickness of the film. Now consider a thin oil film with varying thickness. When the film is of the thickness such that the two waves of red light undergo constructive interference, the film will appear red at this location, and the same is true for the other color for different thickness in different location. Therefore, the oil film shows its characteristics multicolor fringes when viewed under white light. This figure is showing a example of such oil film interference. Now we can review the interference pattern. When we know when waves superimpose, the fringes are formed. The fringes are nothing but the distributions of maxima and minima of the energies. So same thing can be done by this thin film, and in this figure it is shown where a schematic of a thin film is presented with thickness of D and refractive index of NF. Considering the normal incidence of the light, we can find out the optical path length, which is 2D by NF of the reflected beam. Actually, the total phase contributions comes due to the optical path length variations as well as the phase changes from the due to the reflection. Now in this case we consider phi 1 and phi 2 phase introduced due to the reflection from the front and rear surface. These phis are determined from the reflections at the interface. So remember, when a wave traveling down a thin string is reflected with a phase shift of pi radian, and it gets inverted at the interface with a heavy string. So a reflected light with when it is fall on the greater refractive index medium, it suffers a phase change of the phi. So the reflected wave from the rear surface travels an extra distance 2D, which is the path difference, before it is superimposed and interferes with the wave reflected from the front surface. And the wavelength in this film is not at the same as the vacuum wavelength, so it will be changed as lambda f, which is nothing but the fractions of the refractive index of the film. Now in this case we can find out the total phase difference, which is delta phi is nothing but the 2 pi by 2d by lambda f plus phi 1 and minus phi plus phi 2 and minus phi 1, which is nothing but the phase introduced due to the reflections from front and rear surface respectively. Now we can find out the conditions of the constructive and destructive interference. Now for the reflected beams, the constructive interference conditions is given here that is delta phi will be integer multiplied with the 2 pi. And for the destructive interference, the delta phi will be 2m plus 1 into the pi radian, where m is an integer and is given the value of 0, 1, 2, 3 and so on. In the transmitted beam, for the destructive and the constructive interference conditions just reverse. So now we can see some practical examples of such thin film, which is most occur in the nature. It is the coloring of the soap films or the soap bubbles. So a soap film is having air, water and air interface. So the film has high refractive index than medium on the either side, which is air. At the first interface, the refractive index increases, and at the second interface, refractive index decreases. So we can find out that clearly the phi 1, the phase from due to the reflection from the first surface will be pi, whereas the phi 2, the phase introduced due to the reflection from the second interface, will be 0 in this case. So we can include this in this formula, final expression of the total phase difference, where d is the thickness of that soap film, and we can easily estimate the thickness required for the constructive interference of the soap films, which is nothing but d, which is not presented here, which is nothing but that d m plus half lambda 0 divided by 2nf, where m is the integer. And the same way, the destructive interference, the thickness required for the destructive interference can be calculated here. So here we can see clearly these d values are directly related with lambda 0, which is the wavelength of the light fallen here. So if lambda 0 changes, automatically d will change and the whole conditions will change. So from there we can conclude that the result will be different for the different values of the lambda, so that we can get the different colors for the different thickness of the soap film. Now another example of this thin film occurs in practically for the coating of the anti-reflections purpose. So we know that lens of the camera, it should get more and more light to give more clarity of the image. So if we can stop the reflections of the from the lens, which is the glass material from the air surface. So we know that an uncoated air glass interface always reflects the 4% of the incident light. So if we use multiple lenses, these 4% and 4%, so we can lose lot of light which should transmitted and form the image. So to stop this effect, the thin film principle can be used in the destructive interference conditions. So this is the schematic given for a thin film coating, which is used for the anti-reflection purpose. And here the conditions is we are here a glass material, here we are air. So we have to give a thick film which is having refractive index in between glass and in between air. So finally we can get, so here higher refractive index compared to this interface. So when light is falling here, it will see the high refractive index here. So the reflected phase due to the reflections will be pi here, that means out of phase. And the same case when light falling here, and it will get more refractive value, which is nothing but the pi here. So total phase will come as 0. So we can find the minimum thickness for the destructive interference, applying the destructive interference conditions as d, which is nothing but the lambda f by 4. Lambda f is the wavelength in this film. So we can conclude here the two conditions, that waves reflected from the two interface should be out of phase in this to satisfy the condition of the anti-reflection coating, and the film thickness d is equals to the odd number of the quarter wavelength of the lambda f. So these two conditions should be satisfied to make practically a anti-reflection coating on over a glass surface or any other materials. So usually these thin film materials should have the refractive index between the air and the glass of the lens. The material which is most commonly used for this purpose is magnesium fluoride. It is having refractive index of 1.37. At the same time, we have to choose the thickness of the film such a way considering the white light, and we have to get the maximum extent of the destructive interference. So we have to choose of this band in between any colors of this band. So that's why if it is seeing the total visible range, we can get in the reflection pattern it will come around the green purple light, and sometimes the color wavelengths, color versus wavelength, if we see, it will come in the green wavelength. So this is the reason the anti-reflection coated lenses sometimes looks purple or green. Thank you.